So DTA curves of a pure compound, they represent characteristic of that compound for physical or chemical changes. So here, using the DTA curve, we can correlate the changes in energy because of the different types of physical and chemical changes that are occurring inside. The change in DTA curve, it further gives us about the melting point, the glass transition temperature, the crystallization temperature of our sample. So here in 11.5, DTA curve of calcium oxalate in oxygen atmosphere has been shown here. Now we see that this curve, it indicates that three DTA peaks. First is here, the first is endothermic in nature, the second peak is exothermic in nature, and the third peak here that is obtained is again endothermic in nature. Now this correlates the TGA data and confirms that the nature of reaction that occurs in, they are endothermic because of the desolvation and decarboxylation, while the exothermic reaction that occurs here is decomposition followed by oxidation and finally formation of stable calcium oxide. So here, from this type of curve and looking into the nature of the endothermal and exothermal reaction, we can talk about the different types of reaction that is occurring inside the sample. So now DTA curves, they have also been used for both qualitatively and quantitatively. So the position and the peak area, they can be used to determine the composition of the sample. So now from equation 11 that we have discussed, both peak area with the heat of the reaction, they can be related. Now here let us say the calibration factor K that has, we can eliminate it, and let us for example we say if A1 is the peak area of known mass M1 and A2 is the peak area of unknown sample having mass M2, then M1 by M2 is equal to A1 by A2, or M2 is simply given as this. Similarly, the heat of the reaction of an unknown sample can also be calculated with a known heat of reaction value. So here one, we have to keep in mind that the calibration factor, it is temperature dependent in DTA, and therefore both, it is always what we are talking is that the reference and our sample, it should be run at identical temperature. So here we see the determination of area under the peak, it has been a subject of very complex task to resolve this problem. So here a method has been illustrated here in figure 11.6. So both the baselines, they are extended to a perpendicular line that is drawn from the maximum of the curve, and the area under the two halves of the curve, they are determined to give the total area. So this is one of the simple ways by which we can calculate the peak area. So the heat of reaction that is observed in DTA, they can has also been used to calculate the delta H value by using the formula delta Hm, that is the molar enthalpy is equal to delta Hr, that is the enthalpy of the reaction, into Mr by M. Capital M indicates the molar mass of this of our substance, and small m, it indicates the amount of sample that we have taken for DTA analysis. So that is how we can calculate delta Hm. Then coming to determination of heat capacity. So heat capacity, it can be also conveniently studied from a DTA curve, and it has been measured by using the formula Cp is equal to K into T2 minus T1 by small m into H. So here small m is the mass of the sample that we have taken, and H is the heating rate, that is the rate of heating the sample, and K remains the calibration factor, and it is known, it can be determined by calibration against a known standard substance. So construction of phase diagram, here the melting point can be recorded by DTA curve for a eutectic mixture of different sample. These melting points can be used to construct a phase diagram. The critical temperature of organic compounds can also be known. The Curie point temperature, that is called it as the TC. So here it can be also studied from this phase diagram using DTA curves. So Curie point for is has been found to be 357 degrees for nickel, simply by plotting dq by dt versus dt against the temperature, dq by dt against temperature or only dt by t. So in this way we can calculate the phase diagram or know the Curie point, that is the TC for different types of elements. Then estimation of transition temperature. So the precise determination of transition temperature, it can also be known, the temperature estimated, we can say Tm, that is the melting temperature, or boiling temperature Tb, they can be known. Like here it is shown in figure 11.7. We have it different temperature of the DTA curves. It shows different types of temperature. So TB has been most often selected from the portion of the graph. Here it has been shown. So in the figure, first a baseline we draw that meets the both the temperature ends of this graph. So first a baseline is drawn. So then we see the intersection point. The first intersection point here is A. This is the A is the intersection of the extrapolated straight line of the slow temperature side of the peak with the baseline. This B represents the inflection point of the low temperature side, and C is the extrapolated peak here, where D is the extrapolated return to the baseline. So the melting temperature, that is the Tm, it is measured by using the sample is closest to the temperature of point C here, and temperature B at the reference. In exceptional cases it may be D, but in most of the cases the melting temperature is measured by using the sample is closest to the temperature of point C. So this is how we can we can know various parameters from DTA curves. Then various applications of DTA, they have been used in qualitative and quantitative identification of minerals, like oxidation of organic materials has been shown. Here we can see DTA curves for kaolinite, montmorillonite, and illite. Three different types with three different temperatures. The exothermic and endothermic natures processes, they are different. So in this way, we can see, however, we can actually understand how to identify the different types of elements that are present in a mixture. So here in this figure, there is that this figure also has certain limitations. Is that we just looking into the graph, we can uh, the the peak area, it has to be known for identification of the pure mineral identification. But the limitation is the, if we combine these three plots, there is a possibility of the overlapping of different peak areas. So what we do is, here it has been shown, if we combine the overlap the plots, we see there will be identification becomes difficult. So in such cases, to rather simplify the process, individual identification, that is rather than overlapping, we see that some the will classify the temperature regions, and then we will find out what suits to our material. So then here is the, for polymeric materials, DTA actually has been very useful for polymers rather than any other class. It has been used to identify the crystallinity, the TG, the TM, the phase equilibrium, even the degree of crystallization for polymeric materials. So here in this case, if you see the DT of a polymeric sample, this is the TG, this is the TC, that is the crystallization, this is the TM, and T oxidation represents the TD. So four different stages can be identified from a TGA DTA curve of a polymer. The DTA technique has also been used for analyzing a polymeric mixture both quantitatively and qualitatively. We know that TGA curve can show us the stability of polymers. Even a DTA curve, it can show the characteristic peak of each polymer. So here we can see in figure 11.10, many types of polymers have been taken, and they are all, they show the individual characteristics. This DTA, it shows the presence of all the polymers in this curve. Thus, identifying with their degradation temperature, we can identify the type of polymer that is present here. So here in this mixture, attributing, so looking into this mixture, with relating the degradation temperature, we can say which polymer is related to which peak. So another important parameter that can be determined from DTA is the TG, which is a very important factor in polymer analysis, and it is actually caused by second order. It is caused by the relaxation of the chains in that occurs during the amorphous part of the polymer, and this the first evidence of TG it was provided in 1957. That is, it was first detected by DTA. So as such, this transition it is not associated with latent heat but a very sudden change. So we have this relation, that is Tg by Tm is equal to 0.66. The glass transition it can be obtained using number average molecular mass of the polymer ranging from this equation. So then look, from the plot of Tg by Tg DTA plots we can calculate both the Tg and Tm. The DTA plots have been also used in calculation of the crystallinity of the polymer. We know that a polymer is composed of both amorphous parts and the polymer part and the crystalline parts. So the mass fraction, or here we can say delta HF, that is the heat of fusion of the polymer, and the extra hypothetical crystallinity, that is delta HF star. We can calculate the mass fraction from this, and ultimately the crystallinity chi can be calculated using this value. That these, looking from the plots of DTA, we can also calculate the uh, crystallinity, even degree of polymerization. That looking under the area under the curve, we can find out the degree of polymerization for the polymers that we have been used. DTA has also been used for analysis of biological materials, but the amplification of DTA has been much more in polymer chemistry rather than in biology. So, biological materials that consist of active body, the living parts. So, however, it has always been difficult to analyze those biosamples. So, the DTA curves of four different leaf sample in different oxygen environment, they have been shown to show the degradation effect. So looking at the degradation effect of the leaves, we can identify, we can actually predict the nature of the leaves, or the structural degradation of the leaves occurring in different types of environment. The DTA curves for some materials have also been obtained in static or air dynamic oxygen moisture, so atmosphere. So here what we do is looking at the endothermic and exothermic reactions in of various biosamples, the parts of biosamples in different atmosphere. We can say, talk about the degradation process, the oxidation process, the reduction process, and other process. Similarly, this DTA has also been used in analysis of high energy materials, explosives, ceramics, cements, and pharmaceutical industries. So these are some of the industrial applications of DTS. So with this, we finished the chapter on DTA, and tomorrow we'll start in the next class. We'll start with DSC, that is differential scanning calorimetry.
मैडम
So, uh,
क्लासरूम 2 जो आरसी अच्छे अछंती के अछंती कि से सर सर की मैडम
I don't know. ତମେ ଡାଇରେକ୍ଟ ତାଙ୍କୁ କନେକ୍ଟ କର।
अछंती से तांको सर कि मैडम के अछंती कि आरसी भुवनेश्वर जोड़े क्लासरूम 2
ପଚାର ଆଉଥରେ ଯଦି
सर हेलो सर मैडम
କେହି କିଛି କହୁନାହାନ୍ତି।
ठीक जाने चाहते कोर्स कोऑर्डिनेटर का कांटेक्ट नंबर टिके देने
ଆଚ୍ଛା ଆଚ୍ଛା, ସେଇ ୱେବସାଇଟରେ ମିଳିଯିବ।
अच्छा
ହଁ, ସେଇଟା ତମକୁ ସେଠି ମିଳିଯିବ ସବୁ। ହଁ,
ଆଜ୍ଞା ଆଜ୍ଞା ମ୍ୟାଡାମ ପ୍ରାକ୍ଟିକାଲ କେବେ ହେବ କିଛି
ସେଇ
ଆଇଡିଆ
ତମର ସାର୍ ତମକୁ କହିବେ, ଷ୍ଟଡି ସେଣ୍ଟରରେ ପଚାରିଦେଲେ ସେ ସବୁ
ହଁ ହଁ
ସିଡ୍ୟୁଲ ଦେଇଦେବେ।
ଆଚ୍ଛା ଆଚ୍ଛା ଠିକ ଅଛି ओके मैडम हेलो हेलो